Okay, hello everyone. Let's discuss KSP today, the solubility product constant. So KSP is a measure how do I want to measure measure to the extent to which an insoluble salt dissolves. So I will say, before continuing on with this lecture, that for the KSP chapter, it is essential that you know those solubility rules from Chem 1. If you don't know the solubility rules, you will have absolutely no success in this chapter. So you must remember those solubility rules. So let's say I have a insoluble salt that we would have classified this as an insoluble salt in Chem 1. So let's say I have magnesium fluoride. So this is a solid, so we would expect this to dissociate into ions. And this is an equilibrium because the ions can go back and forth from the solid form to the aqueous form because it's a dissolving. It's now become aqueous, these ions. So I'll get a magnesium ion and two fluorine ions. We, like I said, we would normally expect this salt to be completely insoluble where there would be no dissociation into ions. However, KSP tells us that these salts dissolve to a very small extent, some larger than others. So KSP is once again another measure of equilibrium. And in this case, once again, it tells us the extent to which an insoluble salt dissolves, but it's the same thing. It's products over reactants. Now, one thing to note is usually what you're ending up with as your KSP expression is just the products because you're starting off with no amount of salt that has dissolved. So for example, if I was to write the KSP expression for the salt above, I would say that the KSP is equal to the magnesium ion concentration. Now this is where you have to be careful, times 2 times the fluorine ion, and we square that, okay? So the reason why I'm getting the 2 down here is because if I was to make an ice table, I would find, here, let me move this down a little bit. If I was to make an ice table for this, once again, you don't start off with solid, and I don't have any product here. But when the reaction takes place and it starts to dissolve, I'm going to gain x here and gain 2x here. So at equilibrium, I have x and 2x, and that's why the coefficient of 2 is happening here, in addition to being squared. So that is something that's different with KSP. KSP involves that coefficient being, that term being squared because of the coefficient, but you're also going to put a 2 in front of the x. So that's a little bit different. So if I was to simplify this and put it in terms of x, I would have that the KSP is equal to x times 2x squared. So do your algebra here, just be a little careful. So 2 squared is 4. So this becomes times 2x squared. Now I could simplify this. Nope, I didn't need to write it like that. I just wrote the same thing. So if I simplify the expression above, I get 4x cubed. So 2 squared is 4, so that's where the 4 is coming from. The x cubed is coming from the fact that when I square this term right here, I'll get 2x squared, multiply that times another x, and you get x cubed, okay? So that's just a little bit about the math. Now, one term we have to define is molar solubility. And molar solubility is actually what the X is in all these KSP ice tables. And it's the equilibrium position in terms of molarity, or another way of saying that is moles per liter. So in this case, this X right here is equal to the molar solubility of the salt. So the higher the KSP, the more soluble the salt. So this does make logical sense, right? So we said that KSP is the measure to which an insoluble salt dissolves. So if you have a big KSP, that means the salt is dissolving a lot. Well, all of these are very small, but a lot on the grand scheme of small. If you have a very, very small KSP, the salt is not very soluble. It's not dissolving very much. So this kind of does make intuitive sense. So let's do an example of solving for the molar solubility of a compound. So let's say that the KSP of copper 2 iodide is 1.4 times 10 to the minus 8th. What is the molar solubility of CuI2? So the first thing I want you to do when you're doing these problems is to write the dissociation of the salt. So that's what I'm going to do. So I have CuI2 solid, and that's going to break apart into copper 2 ions and this is a little messy, copper 2 ions and 2 iodide ions. From there, I make the ice table. So this is always going to be nothing. I'm going to start off with no product, but when the salt dissolves, I'll gain X here, and I'll gain 2X there because of the coefficient of 2. So this becomes X and 2X. I make the KSP expression. So notice that I have no reactants here, so it doesn't have to be. So it's going to be that product, just the products multiplied. So it would be X times 2X. And remember, we square this because of the coefficient of 2. So it contributes to the 2X, and it contributes to being squared. So we can rewrite this a little bit nicer without the brackets as X times 2X squared. So this, like I said, people will make some algebra mistakes here. So I'm going to try to take it a little bit slower. So I'm going to square the 2 right here. And when I square the 2, I also square the X. So this becomes 4X squared. And now I'm multiplying that by X. So that becomes 4X cubed. And that's equal to the KSP, which was given, is 1.4 times 10 to the minus 8th. Now I need to solve for X. So what I'm going to do is I'm going to divide both sides by 4. So I get 1.4 times 10 to the minus 8th divided by 4 is equal to X cubed. Now in order to get rid of the X cubed, I need to take what's called the cube root of this side. Okay, so it's not the square root, it's the cube root. So on your calculator, there's a button. If you go, well, I'll show you guys, but there's a button that you can find that allows you to type in any integer into the square root, and you can type in a 3, a 4, etc. So you need to take the cube root, and we get that X is equal to 1.5 times 10 to the minus 3rd molar. So this is the molar solubility of the salt. Okay, so let's move on. If I can get my computer to work here. Okay, so let's do a more conceptual example. So let's say I asked you to put the following salts in order of increasing solubility given their KSP. Very common problem you will see. So let's say I have the salts I don't know, making this up on the spot, magnesium carbonate, and that has a KSP equal to 8.7 times 10 to the minus 9. Let's say I have barium hydroxide, which has a KSP equal to 8.9 times 10 to the minus 12. This is, I feel like I said the wrong number there. But anyway, let's say then I have, I don't know, zinc chloride, and that has a KSP equal to 1.6 times 10 to the minus 10th. And then I have copper 2 bromide that has a KSP equal to 4.6 times 10 to the minus 6. Okay, so what do we do here? So the problem is that the KSP alone is not enough to justify how soluble a salt is. What we really need to classify a salt solubility in comparison to another is the molar solubility. Okay, so we need to find the molar solubility of each of these salts. So what I'm going to do is I'm going to make the KSP expression for each of these salts. So rather than go through that whole ice table process, I'm just going to go straight to the KSP expression. I'm going to walk us through it. So notice that when this magnesium dissociates, you get a magnesium, when this magnesium carbonate dissociates, you get a magnesium ion and a carbonate ion. Okay, so this is going to come out to be X times X. If I simplify that, I get X squared. And I can set this equal to the KSP. And here, X is equal to the molar solubility. So if I solve for X given this KSP, I would find the molar solubility to be 9.3 times 10 to the minus 5th molar. I'm going to do that for all of these. Here I would get X for the barium, but 2X squared for the hydroxide. I then have a 4X cubed answer, so then the X is going to turn out to be 1.3 times 10 to the minus 4th molar. Here I have X for the zinc, X for the chlorine, turns out to be X squared. I solve the same way, and I get that X is equal to 1.3 times 10 to the minus 5th. Now I have an X for the copper, a 2X squared for the bromine, same thing as the second one, I get 4X cubed, and X is equal to 1.0 times 10 to the minus 2nd. Now these are all in terms of molar solubility now. So the smallest number is going to be the least soluble. The biggest number will be the most soluble. So here the smallest number is the one for zinc chloride. So this would be the least soluble. Next would be, let's see here, the number for the magnesium carbonate. That's the second smallest. The next would be the one for barium hydroxide. That is almost as big as the biggest one. And then the copper 2 bromide is the most soluble because it has the biggest KSP. Okay, so that would be our answer here. So this is a very common question that they will ask. Okay. Next, let's look at the effect of pH on a solution. Actually, I take that back. We need to talk about something else first. So we are going to talk about next the common ion effect. And you know what? I'm going to combine the common ion effect in a video about pH. So I'm going to stop it here and pick it up in another video.